Right, a 3-degree of freedom system. This is merely an extension of what we did for the 2-degree of freedom system. Okay, and you can extend it to n degrees of freedom. Okay. Anything beyond 3 degrees of freedom is laborious stroke impossible to solve by hand. Okay, so you don't need to worry about going through that process for anything more than 3 degrees of freedom. You know, working out the determinant of a 4x4 or 5x5 is not a simple task, and it's not something I wish to test you on, and probably not something you wish to do. Okay, so we're going to limit it to 3 degrees of freedom. And for a 3-degree of freedom system, it's the same process, but what happens is that KD, our determinant of K of the mechanical impedance matrix, end up being, instead of a quadratic, it ends up being a cubic equation. Okay, there'll be omega to the power of 6 in there, or lambda to the power of 3. Now again, that's quite difficult to solve by hand, and so what will happen? It's only solvable by hand if you've got a semi-definite 3-degree of freedom system, because you know, therefore, one of the natural frequencies will be omega squared, okay? Sorry, will be 0. One of the natural frequencies will be 0. And so obviously you can solve that by hand, because you take out the first natural frequency, you end up with a quadratic, which you can then solve in the other way. So let's do an example. Here's my 3-degree of freedom system, okay? I've got mass 1, mass 2 and mass 3, they're all equal to each other. I've got K1 and K2, the 2 springs, they're also equal to each other. And obviously I've got displacements x1, x2 and x3. It's semi-definite, it's not connected to ground with the spring or mass. Obviously it's running on ground, but we don't need to worry about that. We assume the wheels have no mass, and there's no friction, and the springs are linear. Okay. So using the quick method, we can fill up our mass matrix, MMM, down the diagonal. And obviously the stiffness matrix, you've got the same thing. Mass 1 is connected to mass 2 by K. Mass 2 is connected to mass 1 and mass 2 by 2 springs, so it's 2K. And mass 3 is connected to mass 2 by one spring. Okay, and obviously between mass 1 and mass 2, so this box and this box, we've got minus K. Between mass 2 and mass 3, this box and this box, we've got minus K. And between mass 1 and mass 3, there's nothing. So we've got 0 in there. Make the substitution, you plug them in, you get your mechanical impedance matrix. Okay, you should start to see the pattern of what goes on. We end up with, if we've got 1K and 1M over here, we've got K minus M omega squared. And obviously here it's 2K minus M omega squared, and K times M omega squared. And if you remember, the mass matrix has 0 everywhere else, so these remain the same as what was in the stiffness matrix. Now, you're thinking, well, hold on a second. We've got, if we set this to be 1, we've got 2 unknowns. But the thing is, we've got actually 3 equations that we can use to solve those 2 unknowns. And so it's relatively straightforward. But we first need to find our natural frequencies. So again, following the equation in the solution, the formula sheet, you can solve a 3x3 determinant. Okay, we'll go through that in an example, and you can end up getting an equation of motion. It's quite clear that this can only be true if this is 0, or if this is 0, or if this is 0. And so we end up with 3 natural frequencies: 0, K upon M, and 3K upon M. We know by definition it's a semi-definite system, so the first mode must be 1, 1, and 1. Okay, and if you went through the process of sticking in 0 in here and solving for these 2 values, okay, when this is 1, you end up with 1, 1, and 1, and that makes sense. All 3 masses are moving around with no oscillation. When you stick in K upon M, you go through the process. Again, K upon M, the M's cancel, you end up with just K's. You can divide everything by K and you get this. Okay, we've got 3 equations: this one times by this one times by this, and this one times by this. We've only got 2 unknowns. You can solve it, and you find R2, which is the motion of the second mass in the first mode. So that's why it's R2, 1. And the third mass in the first mode, you end up with, you can go through and solve it, and you end up with 1, 0, minus 1. And that's the mode where the first mass doesn't move, okay, but the other two masses are moving in opposite directions, okay? So that's like a 2 degree of freedom system in the sense where the first mass is not moving at all. The process can be repeated with 3k upon m, okay, so you go through and you end up with this again, so the m's cancel, we end up with 1 minus 3, which is minus 2. Okay, here we've got minus 1, here we've got 2 minus 3, so it's minus 1, and so on. And you go through and you find R2, 2 and R3, 2, and you end up with 1, minus 2, and 1. And that's where the two outer masses are moving in unison with each other, but the one in the middle is moving twice the distance, but in the opposite direction. Okay.